inverse a longer nail.
Eugene, I have a question.
Yes.
What if member like this is just a thought. What if member 4 wasn't like symmetrical? Like what if member 4 was not like the deck itself? You know what I mean? Like if you have one
So number 4 is a smaller block, for example, right?
yeah, for example, would the calculation be totally different or
It will not be totally different, but then you have to calculate what? Then you have to calculate the flange failure at the top and the flange failure at the what?
at the bottom?
Bottom. There you go. Right?
Yeah,
There you go.
thank you.
Okay. You look at the flange failure at the top, then look at the flange failure at the bottom. There you go. There you go. Right?
So our conclusion is that the length of the nail doesn't matter.
No. Yeah.
But it has to be greater than 2 and
Yes,
less than.
that's an optimum. There is an optimum. If less than 2, you're wasting time, man, for this structure. Am I right?
Right.
Right. But
if it's just 2.1, it's obviously like just the point isn't going to hold anything.
No. Okay. So there's an optimum. So for this case, so you know that okay, there's a way to calculate it. Okay. I'm not teaching that now. Okay, I'm teaching on the shear flow. There's a way to calculate. But if there's a nail like for this configuration, is you can buy a nail that's 3.5, you can buy a nail that's 4. What will you buy? So I also I also thought the same. Okay, I'm going to buy 4. Okay, 4 longer, better. I'm going to hammer it deeper. No, don't really help at all. What is more effective is thicker nails. So it's friction based, yes or no? Right? The thicker nail, the bigger the diameter, more force is required to pull out the nail. Okay, because of hydrostatic pressure, which I'm not going to go into that. Okay, this is where it's interesting. I also thought the same. Hey, I'm going to buy a longer nail. Then when you put longer nails, it's like again the joints are separating. So you're like this is not going to help. Or sometimes you decide to do something different. You decide to put a glue, right? Glue it and then nail it. That will help better than longer nails. Yes or no? Okay, this will help you make decision. Okay, so these are the calculation that I do for the city. I done a few for city of Burlington, quite a few in Hamilton before, and 1 or 2 in Toronto, where someone decided to build a high deck, okay, 6 feet long at least, and load bearing. Okay, so I have to analyze exactly what I'm teaching you now. Is it difficult? The answer is no. Okay, because a lot of time the landscaping companies, they are only dealing with aesthetic and build. They don't calculate. The standard rule is what? 6 inches. But why? It can be less. Okay, it can be more. Okay, right. Any questions so far? Let's look at another.
We briefly mentioned velocity. If I shoot that nail in really, really fast, will that increase the frictional force that it holds?
When you increase the velocity, when you shoot the nail, when you have higher velocity, the strain of deformation, if it's on wood, not necessary. It depends on the deformation, okay, of the wood. So it's going to affect, but it's not going to be very significant. For other materials that is strain hardening sensitive, yes. Okay. For wood, no. Okay. Right. So you hammer it mechanically, or it's not going to be any difference. Okay. So the next thing that we're going to look at is we're going to look at the example number 3. Okay, so we're going to look at example number 3. So only on page 2. So example number 3. So now you have a different beam. You have seen this beam before because I've drawn this beam before, okay? The cross section of this beam. Right. So this is as I said, you have seen this before because I think I've drawn this before in one of our lecture. Either, is it this one? No, it's in this lecture, right? So I've drawn where we started longitudinal shear. There you go. So you have briefly seen this cross section before, right? I've drawn this before, that's why it looks somehow familiar. So now the beam is made of a 4-board nail together as shown. Okay, if the nail can support a shear force of 100 pounds, so we know that this is our resistance force. So this will be equal to 100 pounds. Okay. So what they want us to determine is they want us to determine S and S prime, the spacing, right? And given that the shear V is equal to 700 pounds. Okay. So we are given the Vy direction is 700. So if I'm going to draw our transformation X, Y, okay, and Z. So I'm going to write down what is our IZZ. So our IZZ questions like this in your term test, you'll be asked to find IZZ, okay, but I don't want to waste time down here. So 337.43 inches to power 4. And the Y bar from the top is equal to 3.3548 inches. Okay, so that is from the top. Okay, so I'm going to sketch the cross section out. So this is how the cross section looks. Then I'm also going to sketch the shear flow. I think my stupid computer, sorry, I thought it hang. Okay, so this is our cross section. Right. So we have our Vy over here. And the Q will want to go from the top of the beam, top section of the beam, and go down lower. Okay, so I'm going to have my Q doing this. Okay, so that's how the Q is going to flow, right? So when that's the case, with the V over here, the Q will move here, the top. Okay, so that's how you sketch the Q out. Okay, and you guys are like, oh, this is bloody confusing now. Yes or no? Remember we had the other section. Remember we had this, right? We had a section like this. Remember when we had a section like this? Right? Right? We have a section like this. Okay. So how will the Q flow now? You guys are, right? So if you have a Vy down here, I did this briefly, okay? So the shear flow will always want to reach from the top to the bottom, right? So the only way for this to happen is you have to do this. Does that make sense now? Okay, we are treating the shear flow like fluid flow, period. Okay, I repeat again. We are showing the we are making the shear flow similar to what? Fluid flow. That's why we call it the shear flow. That's the reason. So we can construct the flow, right? Are you okay? Makes sense, yes or no? Right? So now, some of you say, makes sense only to you. Okay, so we are going to start. So we know the distance from here to here, right? So this is our centroid. Okay, And then we have our distance 3.35 for an inch. So we have the so the failure. So we have nails. So it's given to us that we have a set of nails going in this direction. Okay, so we have a set of nails in this direction, another set of nails in this direction, and another set of nails in that particular direction. All right. So now we are going to deal with. So I'm going to call this our small web, or our web, or I'm going to call it small because we have a larger web later on. And this is going to be your top flange. Okay. So the failure from here, we know failure will occur at the joint. So failure will occur either at the small web or at the top flange. Okay, or the top flange. And the formula that we're going to use is equal to Q is equal to force or resistance force per nail. Right? Formula very standard. Divide by spacing. Spacing is what we want to find out. And this is equal to Vy over Izz multiplied by what? Q. Rule number one, V and I are constant regardless of the region. Okay, you don't start, if you don't apply that rule, you will be double guessing. What is our shear force? It's only one side only. Okay, we divide the force into two. Then sometimes you remember to compensate, sometimes you forget to compensate. So that's why I'm drilling to all of you. V and I are always constant. The only thing that changed over here is your Q. Now, let's look at the small web. Okay, let's look at the small web now. Okay, the small web. So the first failure will fail due to the small web. So the small web is going to distribute the shear flow. Okay, so you have left and have right. So the small web Q is equal to width multiplied by depth multiplied by y bar. So over here you have 2 because you have left and right web. Your width is equal to 1 inch. Your depth is equal to 3 inches. The y bar is equal to 3.3548. Well, from the centroid, 3.3548 minus by 3 over 2. Okay, so this will be equal to 3.3548 minus by. Sometimes it's good to turn on your calculator. Times by 3 to 1 is equal to 11.1288 inch to power cube. So once you get this, everything is very straightforward, right? So from here, S, so you have Q will be equal to your resistance force per nail is equal to 100. You have 2 nails left and right. Divide by spacing is S. This is equal to Vy. Do we know what is Vy? 700. Your Q now is 11.1288. And then you divide by your I, which is equal to 337.43. So your S down here will be equal to 200 times by 237.43 divided by 700 divided by 11.1 288 is equal to 8.66. Okay, 8.663 inches. Okay, and in real life, I know it's difficult to measure 8.663, so maybe you have 8.5 inch or you bring down to 8 inch. Okay, so that is for your, so this is for your